All right, we've reached the final test out of the 10 tests for convergence and divergence. This is called the root test. And it's most effective if you have series that have nth powers, 2 to the n, 5 to the n, like I wrote below, or you have nth roots in there. You want to use this test. And it's similar to the ratio test in certain ways, meaning once you do your thing, you compare it to 1. If the thing you get is less than 1, it's going to converge. And again, we don't care so much about the absolutely. If it's greater than 1, you're going to diverge. And if it's equal to 1, then just like the ratio test, the root test would fail. It would be inconclusive, and you'd have to try one of the other 9 tests at that point. All right, so let's see how to use the root test. We'll go from there. What the root test says is that you're allowed to take this a sub n, put absolute value bars around it, and then take any root of it you want. You can call it the nth root. That's just generic. That seems strange. It almost seems illegal, but it's not. This is a theorem. This can be proved. I will not prove it. I'm not even sure I know how. That's more of a college upper-level math class. But we're going to try this out and see what happens. Okay, number 5. Use the root test to determine whether this converges or diverges. Well, first I'd look at this and maybe I'd think about ratio test. But since it says use the root test, and since we have n to the n and e to the 2n, we've got a bunch of exponentials, root test is going to be really the easiest, most slick way to do this. So let me convert. Like several of the other tests in this chapter, the root test involves a limit as n approaches infinity. In fact, you can see why we spend all of chapter 1 on limits, because limits are so essential to success in calculus. All right, what we want to do is we take the summand and we copy it. We don't go up by a power with the n's like the ratio test. We just copy exactly what we had. But then this gets a little weird. We put absolute value around it, and then we take any root that we want. I'm going to take the nth root of it. The reason the absolute values are inside is just so that you'll never have to worry about imaginary numbers showing up. Because, if n is even, you could be like, whoa, what if it's, negative inside? No worries. All right, what happens? Well, the e to the 2n, if you nth root that, will just become e squared. And if you take the n to the n and you nth root it, you're just left with n, or n to the first. Okay, so we have that. Now remember, it's still a limit as n is approaching infinity. If you put the infinity in here, you get e squared over infinity, and that's equal to 0. Then, of course, we always compare what we got to 1. Since 0 is less than 1, the root test tells us that this series is going to converge. All right, as you can see, that took minimal work and it was pretty straightforward. What if I had used the ratio test instead? Because we just got done with the ratio test. You just did a homework on the ratio test. You're starting to feel good about it. Let me show you how in this case, with all those nth powers especially, the ratio test doesn't come out as smoothly. It'll still work all right, but ugh. All right, here's the same thing. I used the ratio test. As you can see in the numerator there in red, I went up by a power. All the n's became n plus 1s. I divided by the old one, which means I had to multiply by the reciprocal. Some things did cancel somewhat. Here, I had e to the 2n plus 2 after I did the distributive property. Here's e to the 2n. Those will cancel, except there's 2 extra e's up top. So that'll be an e squared. You can see that right here. Same thing's going to happen eventually with the rest of this. This will come down. Oh, man. N to the n, I can't really cancel with n plus 1 to the n plus 1. They're different exponents, different bases. I just have to leave that alone. Although I can rewrite it using algebra. Since these are both to the n powers, I can take the nth power out and have a fraction. Oh, man. If n is infinity, here I get e squared over infinity, which is 0. Here I have infinity over infinity, and this is infinity. I have 1 to the infinity, so I have to go back and do L'Hopital's rule. I got a natural log both sides, all that good stuff. 5-10 minutes later, it comes out to 1. I'll save you from doing that. 0 times 1 is 0. And then the rest is the same thing as the root test. Oh, since 0 is less than 1, because you always compare it with 1, it converges. Blah. All right, so again, you don't want to do that. If you see problems that have n's in the exponent, especially if there's more than 1, you want to do the root test. Will other tests work? Yeah. But man, the root test is the one you want. And you can see that when I redid number 5. All right, just a few more examples. Let's try number 6. All right, use the root test to figure out whether it converges or diverges. Well, heck, I see that the whole thing's to the nth power. Even if I didn't tell myself to use the root test, that's the test I would have picked. Okay, here goes. It's the limit as n approaches infinity, as always. Take this entire summand and just write it exactly as you see it. Just for technicality's sake, I'll throw absolute value around it. And then you nth root it, which is okay to do. Well, the nth root's just going to cancel out the nth power, just like square root would cancel out squared and cube root would cancel out cubed. Nth root is going to cancel out nth power. And so you're just left with this. And the infinity goes in. And I think with L'Hopital's rule or with your knowledge of pre-calc, you can see that you're heading towards 1/4. That's going to be equal to 1/4. And guess what? 1/4 is less than 1. So the series converges by the root test. All right, I've made one more example of root test. Here it is, number 7. All right, immediately I see this 2n power and I'm thinking, forget all the other tests. I'm going to do root test. Whether directions tell me that or not, that's what I would lean towards. So it's going to be the limit as n approaches infinity. Keep your summand the exact same way it looks. And with the root test, you can actually use any root that you want. You can put an nth root in there. You can put a 2nth root in if you want to. I'll just stick with an nth root for now. By the way, you may have noticed I left the absolute values off. It wasn't by accident. Because the exponent is a 2n power and n are all whole numbers, I know that the inside is going to be squared or like a positive power. And so for that reason, I don't have to worry about it. I could always probably, just to be proper, put it in. Really, the absolute value does nothing mathematical. The absolute value is just simply there to say, look, don't worry about imaginaries. That's all it's for. All right, so what happens when you take the nth root of something to the 2n power? Well, it becomes to the 2n over n power, so it just becomes squared. And we're allowed to break that fraction up. The laws of limits or the properties of limits allow us to do that. This is going to turn out to be 16/9 with a little assist from L'Hospital's rule. Hey, and since 16/9 is greater than 1, this series is going to diverge by the root test. Let me venture back a few steps. What if you had not chosen to use the nth root, But instead, you'd use the 2nth root, which is probably what I would have done. Well, then the 2nth root and the 2nth power would completely cancel each other out, and you wouldn't have this squared here. And I think you can see that right away, that's just 4/3. Now we don't need the extra stuff. 4/3 is still greater than 1, so this is still going to diverge. So you can use any root that you want in here. You want to use a root that's going to get rid of the exponent. So usually I'll just directly match it. That's the easiest way to go. But I made it just a regular n just to prove a point that whether you get 4/3 or 16/9, it's still going to be bigger than 1. It's not going to change your answer of diverging. All right, so that is it for the root test. Now you know all 10 tests, which is awesome. And that'll conclude the first half of the monstrous Chapter 9. Great job on all 10 convergence divergence tests. I'm proud of you guys, and hopefully this is going well. See you later.